Welcome to this explainer. Today, we're diving into a fascinating micro-mystery hiding right in plain sight on the periodic table. We're going to look at one specific chemical family and explore a totally bizarre structural shift that happens to them when things get a little hot. Think about it. What actually happens when you take a family of elements, ones that look virtually identical on the outside, and subject them to intense heat? You'd assume they react the exact same way, right? Well, the microscopic world absolutely loves throwing us a curveball. Section 1. Meet the Group 5A family. 5 siblings with a shared secret. To solve this little mystery, we've got to meet the suspects first. Nitrogen, phosphorus, arsenic, antimony, and bismuth. As a chemical family, these 5 elements share the exact same outer wardrobe. I mean, they literally all have 5 valence electrons orbiting in their outermost shell. And because of that identical outer layer, they possess remarkably similar chemical flexibility. We're talking shifting between oxidation states from -3 all the way up to +5. Basically, they can gain 3 electrons or share up to 5 depending entirely on the chemical reaction. This perfectly captures their basic family dynamic. Just look at how they transition smoothly as you move down the group from lightest to heaviest. Up top, we start with nitrogen and phosphorus, which are pure nonmetals. Then, as the atoms get chunkier, arsenic and antimony step in as metalloids. Finally, way down at the bottom, bismuth is a true full-blown metal. You can also see their melting points are just all over the place, from a freezing -210 degrees Celsius for nitrogen to a scorching 870 degrees for arsenic. Section 2. The vapor state mystery, under pressure and heat. Here is where the story gets super weird. We know their solid and natural states vary, but what hidden structures pop up when we blast them with intense heat and turn them into a gas? Remember that exact same valence electron structure we just talked about? Well, despite that, these elements completely stop acting like a cohesive family when the heat gets turned up. Instead of behaving the same way, these siblings splinter into totally different molecular formations. Let's track the numbers to see exactly how they break the rules. Section 3. Nitrogen, the diatomic lightweight. Let's start at the very top of the group with nitrogen. It's the lightest element in the family and honestly, probably the most stubborn. The crucial point here is our first number, 2. When nitrogen vaporizes, it strictly goes by the power of 2. In its vapor state, nitrogen fiercely pairs up as a diatomic molecule, N2. And they aren't just holding hands. They are locked together by an incredibly strong triple covalent bond. This triple bond is so ridiculously tough and stable that it usually takes extreme energy, like literally hitting it with an electric spark or an arc reaching 3,000 degrees Celsius, just to bust it apart so it can react with oxygen or hydrogen. It absolutely refuses to be anything other than this tight, lightweight pair. Section 4. The tetraatomic trio. Bulking up. Now watch how this builds with the middle siblings. Phosphorus, arsenic, and antimony. As we drop down the periodic table, the atoms get heavier. And suddenly, the atomicity, the number of atoms naturally clustering together in the gas phase, jumps right from 2 up to 4. Under high temperatures, this bulky trio totally refuses to pair up like nitrogen. They bulk up instead. In the vapor state, phosphorus becomes P4, arsenic forms AS4, and antimony becomes SB4. Rather than simple diatomic pairs, they form complex tetraatomic molecules. They literally need a larger, more complex cluster just to stabilize themselves as hot vapor. What's really interesting here is the stark contrast. On one side, nitrogen refuses to be anything but a tight pair of 2 atoms. On the other side, phosphorus and its immediate neighbors naturally cluster into groups of 4. They have the exact same number of outer electrons, yet their structural blueprint in a gaseous state is completely, fundamentally different. Section 5. Bismuth, the metallic oddball. That brings us to the absolute bottom of the group. Meet bismuth, the eccentric, heavy metallic uncle of the family. And in a totally bizarre twist of chemical logic, our atomicity anchor drops right back down to 2. We went from 2 up to 4, and boom, back down to 2. Bismuth completely throws standard metallic behavior out the window. Usually, when you heat a true metal into a gas, its vapor molecules fly around as single individual atoms. They are monoatomic. But not bismuth. Even though it forms a solid metallic crystal at room temperature, vaporizing it creates a diatomic Bi2 pair. It totally defies the rule of monoatomic metal vapors and ends up acting way more like its distant non-metal cousin, nitrogen. Crazy, right? Section 6. Why molecular atomaticity matters. From micro to macro. At this point, you might be wondering, why does this microscopic numbers game of 2, 4, and 2 actually matter to us? Who cares how many atoms cluster together in a gas? Well, we should, because these structural differences and the unique chemical personalities they create are exactly what make these elements so incredibly useful in our macro world. Take phosphorus, for example. Its unique reactive properties literally drive the tech behind brilliant blue and white LEDs, efficiently lighting up the screens and spaces around us every single day. Or look at antimony. Its unique chemical bulk allows antimony oxide to act as a ridiculously powerful, life-saving flame retardant. Manufacturers actively add it to plastics, wood, and fabrics to drastically boost their resistance to catching fire. And bismuth, those oddball metallic properties we just talked about, give it a remarkably low melting point, making it super valuable in safety applications. It safely replaces toxic lead in soldering wire used for electronics. Plus, it's the exact material mixed with tin to create the sensitive trigger in automatic fire sprinklers. It just melts right away to release the water when things get too hot. So, I want to leave you with this final thought to ponder. If sibling elements that look totally identical on the outside can hide such wildly different, complex behaviors on the inside when the heat gets turned up, what other fascinating mysteries are waiting to be discovered in the chemical world? What other fundamental rules are just waiting to be broken? Thanks so much for exploring this micro mystery with me today.